Hey everyone, welcome to Mulsi Math. Today we will be discussing an example from Schaum's Mathematical Handbook of Formulas and Tables, Schaum's 21.34 to be precise. This tells us that if we have an alternating series of this format, we can actually express it as an integral, which is easier to evaluate than the original series. Certainly check out Mathematical Handbook of Formulas and Tables by Spiegel, Lipschitz, and Liu for all of your integrals and series needs. All right. Let's get started on evaluating this expression here. So it doesn't really require that much to prove. Only the geometric series formula, which I will write down for you. We're going to use the fact that 1 minus x plus x squared minus x cubed plus higher order terms is actually equal to 1 over 1 plus x. This is valid for absolute value of x less than 1. And we're going to apply this to the right-hand side of the expression and show that it reduces to the left-hand side. Okay. Right-hand side of this expression is equal to integral 0 to 1 of du of u to the a minus 1. Here's where we use the series formula. We apply it to 1 over 1 plus u to the d power, which means that we just replace x by u to the d. Everything follows. So it becomes 1 minus u to the d plus u to the 2d minus u to the 3d plus higher order terms. Now we just have to multiply u to the a minus 1 through. We get integrating u to the a minus 1 minus u to the a plus d minus 1 plus u to the, a plus 2d, sorry. U to the a plus 2d minus 1 minus u to the a plus 3d minus 1 plus higher order terms again. And this is something that we know how to integrate. Of course, we know how to integrate u, and we see that there are minus 1s attached to each power. So when we integrate it, we're going to add 1 and then divide by the thing that's left, the coefficient. So it just becomes u to the a over a minus u to the a plus d over a plus d plus u to the a plus 2d over a plus 2d minus plus minus plus minus u to the a plus 3d over a plus 3d. We evaluate this between 1 and 0. Notice that the 0 limit is not going to factor in. It's actually going to be 0 since we have a u here. Everywhere it's 0. And then the 1 term, basically the numerators are going to become 1, leaving us with exactly what's on the left-hand side of the expression here. Namely 1 over a minus 1 over a plus d plus 1 over a plus 2d minus 1 over a plus 3d plus higher order terms in an arithmetic progression. Okay, people, we have now derived the expression, so what can it tell us? What is the purpose of what we just did? Why did I do it? Well, one reason you can say is because I could do it. And then leave it to other people to figure out how to apply it. And you know what? That's partially what I'm going to do today. I'm not going to show you all the applications of this because I don't know them all. I'm sure there are more. Perhaps you can find some more. But I'm just going to show you a few examples that are also in Schaum's immediately after this. So it's pretty important to know these examples. Now we're going to use this expression that we just have here. And we're going to look at a equals d equals 1 to start out with. For this simple case, the series in question becomes 1 minus 1/2 plus 1/3 minus 1/4 plus higher order terms, which we can recognize immediately as the alternating harmonic series. We should already know its value to be natural log of 2 by rearrangement in our calculus courses, but we're going to show that it's that here. Okay, so this is going to be on the right-hand side, integral from 0 to 1. We just have a du here over 1 plus u. Why? Well, we have 1 minus 1 is 0, and then d is equal to 1. Well, we can use a substitution here to write this as d1 plus u, recognize it immediately as log of 1 plus u, evaluated at 1 and 0. 0 doesn't contribute since log of 1 is equal to 0, becoming natural log of 1 plus 1, which is natural log of 2. Excellent. We already knew this one though. So why did I show it to you? Well, it's a useful check to show that the formula that we have here reduces to things that we already knew before. So we can have confidence in the results that we obtain when we use it to evaluate sums that we did not know before. Okay, another one. Let's go with a equals 1, d equals 2. If we do this, we get only the odd terms. So it's going to be 1 minus 1 plus 2 is 3, 1/5, and minus 1/7 plus. Now, everyone should immediately recognize this as the Leibniz series for pi. And of course, we know that there are other methods to evaluate this. But let's see how this one plays out. So, 0 to 1 du over 1 plus u squared. Well, that's a piece of cake. We just recognize the integrand as the arctangent. Easy peasy. Why am I writing my T's like that today? Inverse tangent of u, evaluated at 1 and 0. The 0 does not contribute again since inverse tangent of 0 is 0. And inverse tangent of 1 is pi over 4. Since the angle that has the sine and the cosine being equal to it, at least in this particular branch, is pi over 4. Okay, which we know it's the Leibniz series. So we should have already known that it was pi over 4 before this discussion, since we can use the Taylor series actually for the arctangent to derive this. So it's a closely related method. Now let's do one that we might not have known before. So let's go ahead and look at the case of a equals 1 and d equals 3. When we do this, we have 1 minus 1/4 plus 1/7 minus 1/10 plus higher ordered terms. And this one is similar, except we have a 3 on the bottom instead of 2. Now, this integral is not that hard, but it's much harder than the ones that we've done previously. It would take a whole other board or two to show you how to do this one. So I'm just going to quote the result here. Well, yeah. I'm going to quote a result. The integral dx over 1 plus x cubed has terms that are going to be like minus the log of something plus the log of something else plus the inverse tangent of something else. And these something else's are pretty complicated. There's x's, x squareds involved, and so forth. But when you do this, Wolfram alpha tells us that the value is actually pi squared of 3 over 9 plus 1/3 log 2. And I don't know how to derive the value of the series without this integral personally. If you want, I can show you how to evaluate this integral, but it's just really straightforward calculus 2 argument. Basically, you do the polynomial long division on the integrand, and then you recognize that some terms can be expressed as 1 over something, and then 1 over 1 plus something squared like we had up here. Anyways, let's move on. Another example. A equals 1. No, we're going to look at a equals 2, d equals 3, just for some variety here. If we do this, we'll have the series 1/2 minus 1/5 plus 1/8 minus 1/11 plus higher order terms is now equal to the integral from 0 to 1 of du u over 1 plus u cubed. So it's going to it's the same as what we had before, but we just have a u on top instead of a 1. And Wolfram alpha actually evaluates this to be the same result as the previous series, which is interesting. And until you actually look at the integral itself, you wouldn't have any reason to suspect why that they're true. since when we compute this integral with dx x over 1 plus x cubed is now written in terms like log of the same something minus log of that other something plus the inverse tangent of the third something. So these two terms wouldn't contribute, and well, they don't contribute in either case, and only the inverse tangent does, which is why that's the only term that contributes. And that's pretty cool. We have two results that we didn't have previously. There could be other methods to evaluate this. There could still be other series as well that you can use this integral to evaluate. I don't know them. If you do, feel free to leave some in the comments. If I've missed some examples that are much more obvious than this, feel free to leave those. And if you enjoyed this, feel free to like, subscribe. See you next time.